Alright, in this video, this is a continuation of section 9.2 dealing with probability rules. Okay, so continuing with section 9.2, we're going to determine the probability of event A and B for any events. Alright, let's say we have this. Suppose an experiment consists of drawing two marbles from a jar, one at a time, without replacement. This means we do not replace the first marble that we pick. The jar contains 3 blue marbles, 2 green marbles, and 1 yellow marble. What is the probability that the first marble is blue and the second marble is green? Okay. So in this case, the probability of drawing a blue marble on the first draw would be 3 out of 6. And the probability of drawing a green marble on the first draw will be 2 out of 6. However, given that the first marble selected is blue, then the probability of drawing a green marble would be 2/5. Okay? That's because the first marble was selected, it was blue. That means that there are only 5 marbles remaining. Okay, so drawing a green marble, it will be 2/5. The event that the first marble is blue and the event that the second marble is green are dependent, because knowing that the first marble is blue will affect the probability that the second marble is green. Okay. Although some of the marbles have the same color, they are different marbles. There are 6 marbles to choose from on the first draw and 5 marbles to choose from on the second draw. By the fundamental counting principle, there are 6 times 5 possible pairs of marbles. There are 3 ways to choose a blue marble on the first draw and 2 ways to choose a green marble on the second draw. So there are 3 times 2 ways to draw a blue marble on the green and a green marble in that order. So 3 times 2 of the 6 times 5 possible pairs of marbles have a blue marble and a green marble in that order. So here's the way we calculate this. All pairs of marbles without regard for color are equally likely because the marbles are the same size and feel the same. Then, the probability that the first marble is blue and the second marble is green would be 3 times 2 divided by 6 times 5, or 3/6 times 2/5, which is the probability of selecting a blue multiplied by the probability of selecting a green, given that a blue marble was selected. Okay, so this comes up with a definition here. We're going to let A and B represent any 2 events. Then the probability of A and B would be the probability of event A times the probability of event B, given that A has already occurred. So this probability formula agrees with the one for independent events, because if A and B are independent events, then A does not affect the probability of B, which means the probability of event B given A would be equivalent to the probability of B. So here's an example of this. Mikey has 24 pens in a container. He knows of the 24 pens, he knows 5 of the 24 pens are defective because they do not have any ink. So in part A, Mikey randomly picks 1 pen. What is the probability that the pen is defective? And then in part B, Mikey randomly picks 2 pens one at a time without replacement. What is the probability that both pens are defective? Okay. So on the next slide, you're going to see the solution. In part A, he's randomly selecting one pin, so the probability of selecting a defective pin, okay, and here you're letting A represent the event that the first pin is defective, and B represents the event that the second pin is also defective. So in part A, that event, the probability where the first pin is defective is just going to be 5 out of 24, because there are 5 defective pins out of 24 pins in the container. Or as a percent, by doing 5 divided by 24 times 100 will be 20.8%. Now part B, Mikey randomly selects 2 pins one at a time without replacement, and we want to find out the probability that both pins are defective. In this case, we have to use this formula here. Probability of event A times the probability of event B, given that A has occurred. Well, we already know the probability of event A. That's 5 out of 24. Okay, so now, on the second pull, let's say that it is that it is defective on the first pin. That means that there are 23 pins left and only 4 defective pins. Only 4. So the probability of selecting a second defective pin on the second draw will be 4 out of 23. Okay? Because we can say the first pin was defective, and then the second pin, there's going to be 4 left to choose from out of only 23 pins left, because we're not putting the pin back into the container. Multiply 5 times 4, and then 24 times 23, whatever that fraction is, change it to a percent by dividing the numerator and the denominator times 100%, you'll get 3.6%. That would represent the probability that both pins are defective. Okay. Now let's take a look at this example. Well, problem number 15 on page 523. Suppose the probability of event A is 0.24, the probability of event B is 0.55, and the probability of event B, given that A has occurred, is 0.3. And you want to compute the probability of A and B. So the probability of A and B, that's of course this. The probability of A multiplied by the probability of B, given that A has already occurred. So here I'm going to bring this slide back. We're using that particular definition here for any 2 events. To find this out. So the probability of event A, that's 0.24. That's given to us. We're going to multiply the probability of event B, given that A has already occurred. Well, we already know what that is. That's 0.3. Again, that's given to us. So 0.24 times 0.3 would be 0.072. So the probability of A and B would be 0.72. All right, take a look at problem number 16 on page 523. Says here, suppose the probability of event A is going to be 0.35 and the probability of event B will be 0.22. And the probability of event B given A will be 0.15. And I want to compute the probability of events A or B. Assuming that they're not mutually exclusive events, we need to use this formula here. The probability of A plus the probability of B, and then subtract from it the probability of A and B. Okay, now this one I'm going to do here, I'm going to bring down the probability of A plus the probability of B because I know something else. And I'm going to subtract from it. This would be minus. I also know that the probability of A and B, we just got through talking about that, that's going to be the probability of A times the probability of B given A. So now let's simplify. Well, just substitute here. The probability of event A was 0.35. Plus the probability of event B, that's 0.22. And then minus, and in the bracket, the probability of event A was 0.35. That's going to be multiplied by the probability of event B given A. That's given to us as 0.15. Okay, now I'm going to simplify what's in the bracket. So I got 0.35 times 0.22 minus, if I multiply 0.35 times 0.15, that's going to be 0.0525. If I add the 0.35 to the 0.22 and subtract 0.0525 from it, I will end up with 0.5175. Okay. So that represents a probability of A or B. Okay. Here's problem number 22 on page 523. Actually, I'll go ahead and skip this particular problem right here. Okay, let's go to 52. Problem 52 on page 526. Okay, we're going to omit that particular problem, number 22. Church groups and college sports teams often use 15-passenger vans for transportation. The following two-way table of known injury severity of occupants in a 15-passenger van involved in single vehicle crashes for 1990 to 1992 is based on the federal report released in 2004 by the National Center for Statistics and Analysis. So here, this is what the table looks like. And this is where we're going to be using conditional probability. I'm going to show you how conditional probabilities can reduce your sample size. So here's the problem number 52, parts A and B. Suppose an occupant in a single vehicle crash of a 15-passenger van is randomly selected. In this case, what is the probability that the occupant was fatally injured, given that the occupant was restrained? So, here's how I write this. The probability of an injured person, given that this occupant was restrained. And here I'm going to go back to that table here. Now we're given that the occupant was restrained. So I'm only going to look at the row that says restrained. Okay? The total number that was restrained is 1150. So the denominator will just be 1150 and not the total amount of 3,483. The reason for that is I'm only given that this occupant was restrained. And out of the number restrained, how many were fatally injured? So, restrained and fatally injured, there's only 95. So that means that 95 goes up here. So the probability that the occupant was fatally injured, given that the occupant was restrained, would be 95 over 1150. And let's say I want that as a percent. I'll do 95 divided by 1150 times 100. Let's see, this will be approximately 8.3%. And then part B, what is the probability that the occupant was fatally injured given that the occupant was unrestrained? So, injured given unrestrained. Well, going back to that table, given that the person was unrestrained, that's going to be this row right here that I will only look at. The total number that was unrestrained was 2,333. That 2,333 would go in the denominator. The numerator will have the number that was unrestrained. Out of that 2,333 that was unrestrained, how many were fatally injured? That's the 517. So 517 goes here. And let's say I want that as a percent. 517 divided by 2333 times 100 would be approximately 22.2%. So the probability that the occupant was fatally injured given that the occupant was unrestrained would be approximately 22.2%. So this is just an example of a conditional probability where your sample size is reduced. Okay. All right, next we'll look at how to use a tree diagram to represent and analyze probability problems. Tree diagrams. Okay, the main idea of a tree diagram is to represent the outcomes using branches or line segments, and represent probabilities using numerical labels on the branches. Students should be able to represent sample spaces for compound events using methods such as organized lists, tables, and tree diagrams. So the definition of a probability tree diagram is it is a representational tool for systematically organizing the outcomes and probabilities of probability problems that involve several stages. Now here we're going to demonstrate how to use a tree diagram to represent, analyze, and solve a few probability problems here. Like in jar 1 has 2 marbles and 3 yellow marbles. Jar 2 has 3 blue marbles, 1 yellow marble, and 5 green marbles. As you can see here in this particular illustration. Okay. Now a marble is randomly drawn from jar 1 and then placed in jar 2. Then a marble is randomly drawn from jar 2. What is the probability that both drawn marbles have the same color? So here we can analyze this 2-stage probability experiment using a tree diagram. So as you can see here in figure 6, it's using a tree diagram to list all the possible outcomes of the first draw and the probability for each outcome in this stage. So here the labels for the outcomes at each stage appear at the end of the branch. So the probability of drawing a yellow would be 3/5. The probability of drawing a blue would be 2/5. Then the next figure on the next slide that you will see here, you're going to see there are more branches that are created. Now, given that a yellow marble is chosen from jar 1 and then placed in jar 2, there will be 2 yellow marbles in the second jar and 10 marbles in jar 2 altogether. So the probability of drawing a yellow marble from jar 2, given that the yellow marble was drawn from jar 1, would be 2/10. That's this way up here. And similarly, the probability of drawing a blue marble from jar 2, given that the yellow marble was drawn from jar 1, is 3 out of 10. And it continues on, and so on. The probabilities on the branches in the second stage are what we call conditional probabilities. Okay? To complete the probability tree diagram, we need to list all the outcomes and assign a probability for each outcome. So the outcome y, which means that the first marble is yellow and the second marble is yellow, given that the first marble is yellow. So this is the notation for that. But the probability that the first marble is yellow and the second marble is yellow. And then that will be the probability that the first marble is yellow multiplied by the probability of a second marble being yellow, given that the first marble is yellow. And that would be, in this case, 3/5 times 2/10, which would be 6/50. Or, in this case, 12%. If you were to convert that to a percent. Similarly, the outcome YB represents that the first marble is yellow and the second marble is blue. That means the probability of a yellow marble and the second marble is blue would just be the probability that the first marble is yellow times the probability that the second marble is blue, given that the first marble is yellow. That'd be 3/5 times 3/10, which is 9/50, or 18% in percent. So here we obtain the probabilities by simply multiplying the probabilities along the branches. As you can see, the full tree diagram, each individual outcome, and each individual probability from that tree diagram. So here the event E that both marbles have the same color would be this: 2 Y's and 2 B's, both yellow and both blue. So, if we want to find the probability that both marbles have the same color, we'll do the probability of both yellow plus the probability of both blue. That's 6/50 for the probability for both marbles being yellow, plus the probability of both marbles being blue, which is 8/50. That would add up to 14/50, or 28%. Okay. Now, this next example will illustrate that sometimes you don't need to have to draw the complete probability tree diagram, as I showed you. So, in this example here, let's look at it. A jar contains 4 blue marbles and 2 yellow marbles. Marbles are drawn randomly, one at a time without replacement, until a yellow marble is chosen. So here you want to determine the probability of the following events: that exactly 1 marble is drawn, exactly 2 draws are needed, or exactly 3 draws are needed. Now on the next slide that you're going to see here, only one draw is needed, provided that a yellow marble is drawn first. So the probability of a yellow marble will be 2 over 6. Because you got 2 yellow marbles and a total of 6 marbles in the jar. So that means we expect to pick a yellow marble on the first try 33% of the time. And in part B, as you can see here, the first marble must be blue. Exactly 2 draws are needed. So that means the first marble has to be blue, and then the second will have to be yellow. And this is what the partial tree diagram looks like. So here, the first marble is going to be blue. There are 4 blue marbles, so it'll be 4 out of 6 for that probability. And then there's only 5 remaining. So that's why that denominator is 5. But there are 2 yellow marbles, so that probability of drawing a yellow marble, given that the first marble was blue, is 2/5. Multiply those 2 probabilities. 4 6 times 2/5 would be 8 over 30. As a percent, you'll get approximately 27%. And then, that means here we would expect to pick a yellow marble on the second try about 27% of the time. And then 3 draws are needed. Well, if 3 draws are needed, that means on the third draw it has to be yellow. That means the first and the second draws have to be blue. Okay? Has to be. So on the first try, we get a blue marble. That probability would be 4 6. So that means now you're going to have 3 blue marbles, and now you're going to have 5 left in the jar. So the probability of picking a blue marble, given that we drawn a blue marble on the first draw, would be 3/5. And then the probability of drawing a yellow marble, well, we took out already 2 blue marbles. That means that there are going to be 4 marbles altogether. But there are 2 yellow marbles, so that means that probability there will be 2/4. So that's the outcome. Multiply those probabilities together, you'll end up with 1/5 in simplest form, but as a percent, it will be 20%. Okay. And what that means here is we would expect to pick a yellow marble on the third try 20% of the time. All right, now let's look at problem number 6 on page 522. In this case, you have a tree diagram for an experiment involving drawing colored marbles which is given to you. Here you're going to list the outcomes and the corresponding probabilities here. Okay. Now, starting from here, we're going to go here from blue, B to B. And notice that these probabilities are given here along that particular branch. So from B to B, that's going to be 3/5 times 5/8. Which will end up being 3/8. I've already simplified that. Here, just know those 5's divide out, you'll be left with 3 over 8. And then the next one, from here going from blue to yellow, B to Y. Now that probability there will be, if you start here, that's 3/5. From here, it's 3/8. 3/5 times 3/8. Multiply numerator times numerator and denominator times denominator, that will be 9 over 40. And then next we have from here we go to green to blue, G to B. From G to B, 2/5 times 2/7. This will be, in this case, 4/35. 2 times 3, well, yeah, 2 times 2 is 4, and 5 times 7 is 35. So it'll be 4/35. And then the next branch would be from G to G. So we just multiply along those particular branches here. 2/5 times 1/7. That'd be 2/35. And then finally, from this branch to that branch here, from G to Y. That'd be 2/5 times 4/7. This will end up being 8/35. Okay. So those are all the outcomes and all of their respective probabilities here for this particular case. Okay. All right, now problem number 7 is this. A probability experiment consists of drawing 2 marbles one at a time without replacement. There are 2 blue marbles, 1 green marble, and 3 yellow marbles. The probability tree diagram is shown below. So this is what that tree diagram looks like. Okay. Now, on the next slide are just going to be a few problems that we will look at here for those tree diagrams. Here we're going to determine that the second marble is, determine the probability that the second marble is yellow, given that the first marble is green. Okay. We're starting with part A. That's the probability that the second marble is yellow, given the first marble is green. Well, let me go back up to here. We know we're given that the first marble has to be green. That's this right here. What's the probability of selecting a yellow marble? In this case here, that's just the 3/5, okay? Because we're given that this is green. For a yellow marble, that probability would just be 3/5. And 3/5 as a percent will be just 40%. And that's all we had to do to that particular problem. Alright, now, part B, determine the probability that the second marble is yellow, given that the first marble is also yellow. Okay, so if I was to write that in a particular notation, part B is this. The probability that the second marble is yellow, given that the first marble is yellow. Okay, that's what that says. So if I know that first marble is yellow, the probability of getting the second marble being yellow would be 2/5. So this will end up being 2/5, or I made a mistake here. This should be 60%, because 2/5 is 40%. Okay, 3/5 is 3 divided by 5 times 100. That'll give you 60%. 2/5 is 2 divided by 5 times 100. That'll be 40%. Part C. Determine the probability that the first marble is blue. The first marble is blue, given that the second marble is green. Not given, and. It's and. Okay, it doesn't say given, it says and. So we're looking at the probability that the first marble is blue and the second marble is green. So the way we write that would be this: the probability of the first marble is blue and the second marble is green. So that means we need to do some multiplication here. The probability that the first marble is blue times the probability that the second marble is green. Okay. In this case, let's find blue. That's this right here. That's 2/6. And then the second marble is green. That's 1/5. We're going to multiply those two probabilities together. 2/6 times 1/5. So this is equal to 2/6 times 1/5. And this is going to end up being 2 over 30. And as a percent, this would be approximately 6.7%. That would represent the probability of that the first marble is blue and the second marble is green. Now part D, determine the probability that the first marble is yellow and the second marble is blue. Okay? So now we got this. The probability that the first marble is yellow and the second marble is blue. So again, we got to multiply the probability of getting a yellow marble times the probability of getting a blue marble. And in this case, by looking at that particular diagram, probability of a yellow marble, that's this, 3 over 6. And then the yellow marble being, the next marble being blue will be 2/5. 3/6 times 2/5. So in this case, 3/6 times 2/5, which will give us 3 times 2 is 6, over 6 times 5 will be 30, and then to the nearest, 6 over 30, I think that's going to be 1/5, which is exactly 20%. Okay. Let me just say exactly 20%. So probability of selecting a yellow marble and a blue marble would be 20%. And finally, part E. Determine the probability that the second marble is yellow. So here we need to look at all the probabilities where you get a yellow on the second draw. Okay? Right here, we get the second marble being yellow where the first marble is yellow, so we have to look at the probability for the first being yellow and the second being yellow, plus here's another possibility here for a second marble being yellow if the first marble is green. So we need to add to that the probability of getting a green and a yellow, plus there's one more possibility. This being yellow means the first one can be blue, so the probability of getting a blue and a yellow marble. Okay. In this case, the probability of getting a yellow and a yellow marble, we have to multiply those probabilities here. A yellow and a yellow. That's 6 times 2/5. Plus the probability of getting a green and a yellow marble. Here's a green and a yellow. That's 1/6 times 3/5. Plus the probability of getting a blue and a yellow marble. Here's a blue and then there's yellow. 2/6 times 3/5. Okay. So now we're going to multiply what's in those brackets and simplify. 3/5 times 2/5. That looks like it's going to end up being, I know that's 1/2 times, that 3/6 is 1/2 times 2/5 would be 1/5. Plus 1/6 times 3/5. I know that's going to be 1/2 times 1/5 would be 1/10. Plus 2/6 times 3/5. I know that's 1/3. This will end up being 1/5. Now 1/5 with a denominator of 10 would be 2/10. I know that. Then I add 1/10 plus 1/5 would be 2/10. 2/10, 1/10, and 2/10 would be 5/10, which is 1/2. So that means the probability of, in this case, that the second marble is yellow would be 1/2. Okay. Okay, I have one more example, one more problem that I need to do here. This is going to be problem number 9 on page 522 in your textbook. It says here, suppose you had a jar with 17 red marbles and 23 black marbles. You randomly select a marble from the jar without replacement. If the marble is red, then you add 7 marbles to the jar and randomly select another marble from the jar. If the first marble is black, then you add 13 blue marbles to the jar and randomly select another marble from the jar. Here you want to determine the probability that in part A the second marble is black, given that the first marble was a red marble, and then the second marble is a red marble, given that the first marble was a black marble in part B. Part C, the second marble is a yellow marble, and part D, the second marble is a blue marble. This is where we can construct a tree diagram from this particular situation here. And I've already worked this problem out, so for the sake of time, this is what the tree diagram looks like. In this case here, let me do this here. We start with, of course, red and A, and I'm letting B be black. So, in this case, the R is your red, B is going to be black, and I'm letting BL be blue. BL will be blue. So the probability of selecting a red marble, well, there are 17 red marbles out of a total of 40 because there are 17 red and 23 black. That's a total of 40. So that's 17 over 40. And for the black, there are 23 out of 40, so that's 23 over 40. Now it says here, we select a red marble. we add 7 yellow marbles here. So you see there's 7 yellow marbles here. So instead of having 39 marbles, you'll be down to 39 marbles, but when you add 7 marbles, you're going to have 46 marbles if a red is chosen. So for selecting a red marble on the second selection, you've already drawn a red marble, so you'll be down to 16, but there are going to be 46 left, so it'll be 46. A red marble is drawn, that means that there are 46 marbles here. A black marble, you'll have 23 black marbles out of 46, because the first one drawn is a red. You didn't draw a yellow marble, so you'll still have 7 yellow marbles in that jar out of a total of 46. Now for the black marble, there's a condition saying that the first marble is black, you will add 13 blue marbles here. So that's why you see the BL there. So there are going to be 13 blue marbles in that jar. That means you'll be down to 39 altogether, but you're going to add 13 blue marbles for a total of 52 marbles here. That's why you see 52 in the denominator. So a black marble was drawn, but for the probability for a red marble, you'll have 17 red marbles in that jar. So it'll be 17 out of 52 for selecting a red. For selecting a black marble, you've already selected the first one being black, so now instead of 23, you're going to be down to 22 black marbles out of 52. And of course, for blue marbles, for a blue marble drawn on the second, given that the black one was drawn, would be 13 out of 52. So that's how you create that tree diagram. So now to answer part A, the probability that the second marble is black, given that the first was red. That's this right here. Black marble, given that it's red. Well, if this is red, the probability of giving selecting a black marble would be 23 out of 46. And then part B, the probability that the second marble is red, given that the first marble was black. That's this right here. Well, it's black, but given that the first marble is black, what's that probability of selecting a red marble? It's right here, 17 over 52. And then C says that the second marble is a yellow marble. Well, if that second marble is a yellow marble, then that first marble that we selected has to be has to be red. Okay? Second marble was red. That means the first one had to be, yellow. The second marble has to be red. So this is 1740 times 7 over 46. We just multiplied those respective probabilities here. Now, as a percent, I came up with 6.5%. And then finally, part D. The second marble is the blue marble. Here's the blue marble. If the second marble is blue, that first marble had to be black. So, we multiply these two probabilities here. 23/40 times 13 over 52. This will be approximately 14.4%. Okay. Alright. So hopefully this will help you complete some of the homework problems that are in section 9.1. Do reach out to me by email if you have any questions about anything that's in this particular video. I'll try to do this the best way I can. But, do email me if you have any questions about this particular video. So that's the end of this video for the probability rules section 9.2.